Okay, sorry, this is part 2. Should be picking up right where we left off in the last video. Little technical issues. So what I'm going to have to do here, you can probably see I'm going to have to trace this ray back. And I did not draw that particularly well, like at all. So let me, let me just kind of cheat. Like this ray and this ray are supposed to be the same ray, but obviously that doesn't work out very well for the purposes of my drawing. So I'm going to cheat a little bit. My apologies. But you can see the point of convergence here behind the mirror. And so what I'm going to get here is an image that looks like that. There's one more rule I could use. I'm not going to use it here because it's going to get really convoluted. These two will work just fine. Feel free to use the third one if you want. Again, if you're in my class, it's in Canvas. So if I do this carefully, I trace this back, I find that the virtual rays converge there. I can go ahead and write down that this is a virtual image. Now, let's run the mathematics and make sure everything agrees. Make sure you still see that. Same equation that I've been using. If I want to know, let's let our focal length be minus 10 centimeters. Let's let our distance to the object be 15 centimeters. And I'm looking for distance to the image and magnification. Okay. All right, distance to the image. I've got f dO over dO minus f. That is going to be minus 10 centimeters times 15 centimeters. Make sure you can see this. Over dO minus f, that's 15 minus negative 10 centimeters. What I'm going to get out of this is minus 150 square centimeters over 25 centimeters. Lose one of the units. And I'm going to get minus 6 centimeters. So again, the minus will tell you for mirrors that the image is on the opposite side of the mirror as the object. So check. 6 centimeters, that is smaller than my focal length. Oh, yep, check. There's my focal point right here. Check. I feel good about this. All right, let's look at the magnification. Minus di over do. I get minus 6 centimeters over 15 centimeters. The two negatives are going to give me, not moving that out of your field. Two negatives are going to give me a positive. I get 2/5 out of this, which tells me that the image is smaller than my object. Check. Positive means it's upright. Check. All right. So whether or not you know it, you're really familiar with this. What do I have? A smaller image that's upright. So if I see an image of something that's small, I typically think that the object making that image is far away. If it's a flat mirror, I get a good one-to-one correspondence. But for this, if I see this small image, just because of how my brain works, I think, oh, that thing is small, it must be far away. Well, that's not true. I could be really close to this. So where have you seen these before? Let me give you a clue. Objects in mirror may be closer than they appear. Right? Your passenger side mirror is a mirror of this type. I said we had some large trucks will have these on the driver's side. They're actually little spherical mirrors. It's obvious to see that they are. The passenger side mirror might be a little bit of a harder sell because it's got a much less extreme radius of curvature. It's almost flat, but this is a passenger side mirror. Like I said, they use these a lot in convenience stores because of the diverging nature. You get a wide field of view, and they use them as security mirrors. But that is the diverging case. So we've got all three cases of lenses, all three cases of mirrors.